Hey folks, I have what I think is a very cool problem today. I think it's very cool because the math behind it is interesting, and honestly it's stuff that we'd have to cover this year anyway. But it's really interesting to me because this was something we actually had to deal with, me and another student. I had a student a couple of years ago who was part of the costume crew for one of our plays. And she was tasked with exactly the word problem below, which was she had a skirt where she needed to place 6 buttons on them, and she needed to equally place those buttons as well. She came to me and we worked it out together, so I thought it was very interesting. I suggest you work it out yourself before I go and spoil it for you in this video. So before I get going, this would be your chance to pause it, think about it, give it a shot, and when you think you got it, or if you just give up, come back to the video and go for it. But I'm starting just about now. Seeing as this is geometry and stuff, it's probably a good idea to draw on this somehow. Give yourself a diagram to work with and scribble on. So I know that I'm going to place 6 buttons here. 2 of them are already present, so I want to try to, the best I can at least, equally space 4 buttons in between these. Let's give that a shot. Remember, it's okay to kind of eyeball it here. What we know about these segments is that they are congruent. That's kind of what it means for them to be equally spaced in this case. So I'm going to draw some congruence marks to indicate this visually. And again, if you were to take a ruler to this, you wouldn't find exactly that, but that's okay. This is for computational purposes. If we move on to the next part, we're told that the first button is 2 inches down from the top, indicating that this length is 2. And the last one is 30 inches down at the very bottom of the skirt. So if we know that this first green segment is 2, well then everything else here has to fill up the remaining 28 inches of the skirt. So with that being said, what we know is that these, I guess I should say this first, also knows that these 6 buttons don't make 6 segments. We have 5 congruence marks indicating that there are 5 segments, 5 equal segments, that when you put them together you get the 28 inches. So then if I ask you how far apart must each button be, I'm really asking how long are each of these blue segments? As it turns out, if 5 of them make up 28 inches, then I guess each of them is equal to 1/5 of 28. And however you choose to represent this is up to you. 5 goes in 28 5 times, so the remainder 3. I think it might be easier to work with decimals in this case, so I'm just going to call it 5.6. So each of these is 5.6 units. The next part asks how far down is the third button, which is this guy. So there's a couple things to take into account here. If I'm asking how far down it is, I'm talking about from the top. That deals with the 2 inches to the first button. It deals with the first segment of 5.6 inches, and it deals with the second 5.6 inches also. So the distance from the top to the third button that I'm pointing to in orange is going to be 2 inches plus 5.6 plus 5.6 more inches, which will give you, oh boy, 13.2 inches. I'm about to move on to the next video, or not video, the next slide. Pause this, just kind of soak it in until you're ready for what comes next. So once again, this problem is asking us to partition a segment. That's basically what the last problem was without spelling it out to us. But just as before, what we're looking for here is a point that's going to break up this segment AB into a couple, oh that was terrible, into a couple other segments that are of some kind of given proportion. In this case, we're looking for a point V that's going to break this up into a segment that's essentially 3/5 of the entire thing and also 2/5 of the entire thing, because that's the remaining piece of the entire thing. So again, if you want to tackle this on your own, I would pause right now. I'm going to proceed, and then I'm actually going to give a hint. And if you want to take it from there, if you think the hint has helped you enough to finish it yourself, feel free to pause it again. This is the beauty of doing it with a video. You can kind of go at your own pace. But again, here I go. Pause when you'd like to. So I kind of re-sketched segment AB on the bottom here. Because without the number line, I feel like I can kind of doodle a little bit more without having to worry about any permanence or any illusion of landing on a spot I'm not actually landing on here. But I could fool around with this, and I kind of took a guess as to where V would be approximately, because it looks like it's about 3/5 of the way from A to B, closer to B. And I should really think about what it means to be looking at this in terms of 3/5, or just in general, in fifths. So what this means is I can kind of look at this and say, if I were to kind of chunk this into pieces, it would be best if I worked with this segment in terms of what 1/5 of the entire thing is. You know what? That's my hint to you. So we have AB, And it would be helpful if we could not only find AB, but find what 1/5 of AB is. If we could find out what that number is, we could find out the distance, or the length rather, of each of these humps that I've sketched. And then that'll help tremendously in finding out what the coordinates of V is. So again, if you think this was a helpful hint, and you're going to use it to actually find the answer now, if you couldn't before, pause it and give it a shot. But here I go. Moving on. So AB we can find with relative ease. It's on a number line, so we know the distance from one point to another on a number line is just the absolute value of the difference of their coordinates. Really, in this case, you can just count it out, right? From -6 to 8 is 14. If I perform the calculations, I get the absolute value of 14, which, yeah, is 14. Okay. So 1/5 of that, 1/5 of 14, if I were to represent it like a fraction, 5 goes into 14 twice, with the remainder of 4, 4/5 is 2.8. That tells me that each of these humps is 2.8. So this one is, so is this one, so is this one. So what this means is from A to V is going to be 3 leaps of 2.8. 1/5 of the entire distance from A to B is 2.8. So let's take that into consideration here. I want to start at A, which has a coordinate of -6, and travel 1/5 of the distance, or travel 2.8, 3 times. If I travel 2.8 units to the right 3 times, I'm effectively adding 2.8 plus 2.8 plus 2.8. If you want to clean this up a bit, you can write that as 2.8 times 3, obviously. I'm assuming you could do this arithmetic and see that it comes out to 2.4. So you know what? If I go back up top and I look at approximately where 2.4 is, right around there-ish, that looks right. So remember, looking right isn't everything. It won't help us find the answer, but once we've found our answer, it should make sense in the context of the problem too, which this seems to do. So we've done it. V appears to have the coordinate 2.4 on the number line. Awesome. So notice how on the top this says that this is only part 1. Part 2 would involve partitioning segment in a similar way, but rather than it being on a number line, it's going to be on the coordinate plane. We're starting off with this because the process is very similar, and when we transition from the number line to the coordinate plane, we could draw some connections. It's going to be a lot like what we did with midpoints too, where we just found the average of the two coordinates, and then when we got to the coordinate plane, we did the same thing. We took the average of the x's and the average of the y's. Slightly different process, but it's going to transition in the same way. So brace yourself for that. If you need to go back and look at this, that's fine. It's a video. And if you need to talk to me and you need help or anything, go for it. But until the next video, take care.